SwayamPrabha. Digital India. Educated India.
Hello all, welcome to week 8 of the course where we will be discussing on the macromechanics of the lamina. In the previous week we discussed about the stress strain relations for a general 3D anisotropic material. We also showed how can we simplify these stress strain relations by considering symmetries available with the stress and strain or at the material level. But in this week we will be coming back to the composites. We will look at an orthotropic material, especially a single layer of orthotropic material which we call as the lamina. So, for this lamina we will be studying the macromechanics. So, earlier we mentioned what macromechanics means. It means that we are assuming this lamina is a homogeneous material which has effective properties. So, though the lamina is composed of the fibers and the matrix, we now assume it to be as a homogeneous material which has effective properties. So, now the idea is how to use these effective properties to know what are the stresses or the strains at different parts of the lamina. So, in this video specifically we will be focusing on the specially orthotropic material. I hope we remember what specially orthotropic means. It just means that the material has principal coordinates along the axis of the fiber and perpendicular to it. But if our choice of coordinate system is aligned with these principal material coordinates, that is when we call it as the specially orthotropic material. So, for this specially orthotropic material we will show what are the stress strain relations, but this time we will show it for 2D state of stress, meaning we will only show it for plane stress state. Okay. So, here is the strain stress relations for the specially orthotropic material, where we said the coordinate system chosen is aligned with the material coordinates. So, in this special case we see that few of these components go to 0, mostly this shear extension coupling as well as the shear coupling. So, these two couplings go to 0 when we consider this specially orthotropic lamina. Here we notice that there are 6 components of strain and the 6 components of stress related by this 6 by 6 matrix, but since we have seen it is a symmetric matrix as well as few of the terms go to 0, effectively this compliance matrix is defined by only few elastic constants such as the elastic constants E1, E2, E3, Poisson ratios nu1 2, nu2 3 and nu3 1, and the shear moduluses G1 2, 2 3 and G3 1. So, effectively we have 3 for these elastic modulus, 3 for Poisson ratio and 3 for shear modulus. In total we have 9 elastic constants. We define the stress state in the specially orthotropic material. Okay. So, this is the backup or review of what we have discussed in the previous lectures. But now let us see how we can further simplify these strain stress relations. So, when we consider plane stress, so usually laminas, as we know, the thickness of the lamina is very small compared to the dimensions of the lamina. So, it is a general practice to consider it as a plane stress. So, lamina is usually but what do we mean by plane stress? We define it when the out of plane stresses go to 0, which include sigma 3 going to 0 or tau 1 3 and tau 2 3. When they all go to 0, that is when we define it as a plane stress. So, for laminas we can safely assume it to be under plane stress. So, which further simplifies the strain stress relations. So, here we can show that the sigma 3 goes to 0, tau 23 and tau 31 also goes to 0. So, we are left with 3 components of stress. So, now let us see how we can relate these 3 components of stress with the 3 components of corresponding strain. So, here we write the 3 components of stress sigma 1, sigma 2, tau 1, 2, which are the only non-zero values, and then the corresponding strains we again have 3 components which are epsilon 1, epsilon 2 and gamma 1, 2. So, these are related with the compliance matrix. Here we will call this S as the laminar compliance matrix. Now, let us see what are the components of these compliance matrix. So, S11 by looking at this 6 by 6 matrix we can write it as 1 by E1. S12 is minus nu 21 by E2, which can also be written as nu 12 by E1. Okay. And what about this S66? S66 can be written as in terms of 1 by G2, G12. And finally, S22 is 1 by E2. So, these are the non-zero components of the laminar compliance matrix which we have shown here. So, let us see how many non-zero compliance components do we have? We have 5 non-zero compliance components. Because we also need to include this S21, that is how we get these 5 non-zero compliance components, out of which we know that only 4 are independent, since S12 equals S21. This is coming from the symmetry of the compliance matrix. We can now say that there are only 4 independent compliance components, of which this can be written in terms of how many elastic constants did we use to write these components. We have used 4 elastic constants. Which include the E1, E2, G12 and nu12. So, in summary, we can now see for a 2D state of stress or the plane stress, we should be able to write the strain stress relation in terms of the laminar compliance matrix S. And this compliance matrix it written in terms of the elastic constants E1, E2, G12 and nu12. Now, let us move on and see how we can write the stress strain relations. For the stress strain relations, where we have 3 components of stresses and the 3 components of strains, we now use the Q matrix, which we call it as the laminar stiffness matrix. Bear in mind earlier when we were referring to the stiffness matrix, we used the matrix C for 3 dimensions, but when we come to the 2 dimensions, we come up with a new terminology where we use Q to refer to the stiffness matrix. Okay. But now let us see what are the components of this stiffness matrix. So, Q11 can be written as E1 by 1 minus nu12 nu21, and Q22 can be written as E2 by again the same denominator nu12 times nu21, and Q66 is G12 and Q12 is given as nu12 times E2 divided by 1 minus nu 1 2 times nu 2 1. So, with these 4 components we should be now be able to define this laminar stiffness matrix. So, effectively in this slide and in the previous slide we are able to show the relations for stress and strain as well as the strain stress relations for plane stress conditions. But bear in mind we are only discussing about the specially orthotropic materials, meaning the choice of our coordinate system is perfectly aligned with the material coordinate systems. So, let us summarize what we have discussed in this video. So, we started with the general state of stress for a specially orthotropic material where the coordinates match with material coordinates or the principal coordinates. So, for to define this 3D state of stress, we had 6 components of the stresses and the 6 components of strain related with the stiffness of the compliance matrix. But when we moved to discussing about lamina, we said usually lamina can be treated as a 2D state of stress or a plane stress, where the out of plane stresses components go to 0, like sigma 3, tau 1 3 and tau 2 3, they all go to 0. But when we have this, we said the strain stress relation can be now shown as strains in the principal coordinates is written in terms of the compliance matrix S times the stresses again in the principal coordinates. And similarly for the stress strain relations, we said stress in the principal coordinates can be written in terms of the stiffness matrix. This time we will be using Q to denote this 3 by 3 matrix times the strains in the principal coordinates. So, this should summarize the stress strain relations we need to apply for 2D state of stress or the plane stress of a lamina. So, in the next video we will look at if the material coordinates we have chosen are different from the coordinates axis, how the stress strain relations change. So, in other words, instead of looking at a specially orthotropic material, we will start looking at a generally orthotropic material which is most common in general applications. See you then.